Hey there, in this video, we're going to be going over some equilibrium constant practice problems having to do with some ice tables and some calculating equilibrium constant and some Lacombes principle. So let's jump right into it. Here we have, consider the reaction of 3A plus B yields C or 5C plus 2D. In a 5-liter container, the reactants and products are at equilibrium. There are that many moles of all of the different reactants and products. What is the equilibrium constant? So I'm going to be pretty brief in this video. I'm not going to calculate all the final answers, but just tell you how to do it. So for the equilibrium constant, the best thing is to always write the expression first. So Kc is going to equal the concentration of the reactants, the concentration of the products to their coefficient power divided by the concentration of the reactants to their coefficient power. Now, the only reactants and products that count are the ones that are in either the gas, that's not a G, the gas or the aqueous state. And the reason why is because those can mix together with other gases or aqueous components, making a solution. Where you have solid liquids or pure liquids and pure solids, they cannot form solutions. They are just pure substances. So we see right off the bat that B, the reactant, and then C, this product, both are in the solid form. So we cannot include those in the equilibrium constant. So that leads us to writing our constant with our only product being in the gas form as D, as 2D. So that means it would be the concentration of D squared over the concentration of our only reactant that's in the gas form, which is A cubed. So then what we would do is we need to convert our molar values that are given, which is the mole amount, into concentrations. That's very easy to do because we're given the liters. So the total volume of the container. So if you have 0.3 moles of D, that means you have 0.3 moles divided by 5 liters of D. You would square that number, and that would be over the concentration of A, which is the molar amount of A, which is 0.44 divided by 5 liters cubed. And whatever that answer is going to be your Kc value. And you can post it in the comments below if you want. You could put like number 19 and then put the answer. All right, moving on to the next one. We have at a certain temperature, the equilibrium constant is 305 for this reaction. Calculate the equilibrium constant for this reaction. All right, so let's see what the modification is between reaction 1 and we call it reaction 2. So reaction 1 is, you can see that the reaction 2 is half of reaction 1. So you're going to multiply. So what you have here is our equilibrium constant for reaction 1. We can call it as Kc1 equals 305. Now, if you multiply a reaction by a constant, in this case, the constant is going to be multiplied by 1/2. What that means is the corresponding equilibrium constant needs to be put to that power. So our Kc2 would be Kc1 to the 1/2. It wouldn't be multiplying it by 2 like we see in Hess's law. It would be to the 1/2. In other words, the square root. So the square root of Kc1. So we can calculate the square root of Kc1, which is the square root of 305. And this one, I will calculate it because it won't take too long. And it is 17.5. All right, moving on. We have phosgene is formed from carbon monoxide and chlorine using this reaction right here at 612 Celsius. Kc is approximately 17.9 per molar. And calculate Kp in per atm at this temperature. So we want to convert from our Kc value to our Kp value, which is given in this equation. So Kp equals Kc times RT to the delta N. So in this case, we want to establish our R constant because we're dealing with ATMs here. Our Kp is going to be, instead of molarity, it's going to be in ATMs. So we want to have that in our ATM ideal gas constant, which is 0.08206. That's not right. 0.08206. 0.08206. Now our temperature has to be in Kelvin. We're given that our temperature is 612 Celsius. So we are going to solve for that in Kelvin by adding 273, which is going to be 885. Now our delta N, which is our change in moles from the products minus the reactants. So our product moles is going to be 1. Our reactant moles is going to be 2. So 1 minus 2 is going to be -1. So we can have our expression for Kp, and it's going to be Kc, which is 17.9, that's given, times our R, which is 0.08206. Oh, this should not be in parentheses. Or we should not close the parenthesis yet. Times our temperature, which is going to be 885, and to the -1. So again, I'm not going to solve this one, but you guys can write it in the comments. We can call this number 3. We'll call it number 3. And you can write the answer in the comments if you'd like. Moving on to the next one, we'll call this number 4. Consider the value, or consider 1.5 moles of carbon monoxide and 2.4 moles of chlorine sealed in a 7-liter container at 476 Celsius. The equilibrium constant of Kc is that. Calculate the equilibrium molar concentration of CO. So to me, this sounds like an ice chart where you're looking for some kind of equilibrium concentration, or even if it's you're given initial values and you're asked to calculate a equilibrium concentration or a Kc value, it's usually going to be an ice chart. So we want to write the equation up here. Cl2 yields COCl2. Now our initial, and keep in mind, we're talking about initial concentration, not initial molar amount. So initial concentration of carbon monoxide is going to be 1.5 moles divided by 7. So 1.5 divided by 7. For Cl2, it's going to be 2.4 divided by 7. And for COCl2, it's going to be 0. So now, since all of these coefficients are 1 and it is balanced, we have for our reactants, it's going to decrease as it goes in the forward direction, minus x, and plus x. And then our equilibrium concentrations are going to be 1.5 divided by 7 minus x. And then we're going to have 2.4 divided by 7 minus x. Then we're going to have just x. All right, so then we are asked to calculate the equilibrium molar concentration for CO. And we're given Kc. In order to do this, we want to calculate the value for x. So we can write the expression for Kc. And let's just write the general expression over here. Kc is the concentration of COCl2 at equilibrium divided by the concentration of CO at equilibrium times the concentration of Cl2 at equilibrium. And we can convert this into our numerical values of, since we know what Kc is, it's given, it's going to be 2.50 equals the concentration, which is going to be x. So we're looking at our equilibrium concentrations here for this part, times our concentration for CO, which is what we're looking for. So calculate the equilibrium molar concentration of CO. And it's in terms of x. So we're going to have to solve for x. That's how you know x is your goal. And then we're going to have the concentration of Cl2, which is 2.4 divided by 7 minus x. Now you can solve for x using a quadratic formula, and you can get your answer. I'm not sure what the answer is, but I'll leave that to you, and you can comment the answer below. Okay, for the next reaction, we have this given reaction. Initially, a container contains 0.89 molar of HBr and no product. What is the equilibrium concentration of HBr if the equilibrium concentration of H2 is 0.11? So this is another form of an ice table question, because you have something that's missing. They could give you different information. So basically, these problems are identical. They're all the same, but they give you different pieces of information. So here they don't give you the equilibrium constant, but they give you equilibrium concentrations of one thing, of one of the reactants or products. So let's just solve it like we normally would. Initially, the concentration of HBr, 0.89. And then all the products are going to be 0. Because it says initially a container contains, and it says no product. Sometimes they might not even say no product, But if they say initially it contains only one thing, you could assume the others are 0. All right. So, or at least you can assume the products are 0. Now, what is the equilibrium constant? Well, it doesn't matter what the question is asking for. We can figure it out. So our change is always going to be the same. We have our, or as we've been doing. So we have a reactant is going to be decreasing by 2x because our coefficient is 2. Our products will be increasing by x because their coefficient is 1. And our change is going to be 0.08, nope, 0.89. 0.89 minus 2x. Then you have x and x. But we are given another piece of information, that the equilibrium concentration of H2 is 0.1. This is the equilibrium concentration value or expression that we got for H2. That means simply x equals 0.11. And you can figure out a lot knowing x. You can figure out the equilibrium constant. You can figure out the equilibrium concentrations for everything else, etc. So that's what it's asking you to do. But it's saying that what is the equilibrium concentration for HBr, which we can take this 0.11x and put it into here. So it would be 0.89 minus 2x, which is 0.22, which is 0.67 molar. So that's how you would solve for that one. Now for this one, we have another ice table problem. So initially, a container contains all this stuff at equilibrium. The key is at equilibrium. So we're already at equilibrium. What is the new equilibrium concentration of H2 if the concentration of H2 is increased by 0.164? So let's write our equation. 2HI, oh, that's weird, yields H2 plus I2. And we're going to draw our ice table, ICE. And now we have different things. So we have at equilibrium, we have 0.6, 0.038, but we're not going to write that now. And then I2 is going to be 0.15. So before we begin this, let's talk about Lachatier's principle. So Lachatier's principle, which there are some examples in the next couple slides, basically what happens is if you're adding reactants or products, or let's say in this case products, because that's what you're doing. With H2, you're adding H2, you're adding products. Lachatier's principle talks about an equation at equilibrium as a balance. If you add more to the product side, what's going to happen? What's the reaction going to want to do in order to restore that balance? The reverse reaction, which will go this way, is going to take precedence and be faster than the forward reaction in order to restore equilibrium concentrations. So that is what's going to happen in this case. The reverse reaction, rather than what we've always seen in what we've always seen in ice charts is where the forward reaction is occurring. The reason why the forward reaction always occurs, or we assume that, is because there's no products. In this case, we're starting out with both products and reactants, and we're saying there is going to be even more stuff added to the products. So the reaction occurs in the opposite direction. So it's very important. That means our ice chart will kind of be the opposite. So let's take that into here. Our H2 initial value is not going to be 0.038. It's going to be 0.164 plus 0.038 plus 0.164. That will be our initial concentration because you're taking what originally was at equilibrium and you're adding that amount. And that is actually going to be 0.202. So now for the change, remember, we're going in the reverse reaction because now we have more products than the equilibrium constant requires because we heavily stack the product side with more H2. This means the reaction will go to the left, which means the change in HI, which is a reactant if you talk about the forward reaction, but since we're talking about the reverse reaction, it is now a product and it will increase by plus 2x. H2 will decrease by minus x, and I2 will also decrease by minus x. And then we solve it just like we do for a normal equilibrium ice chart. So we do 0.6 plus 2x, And then for H2, 0.202 minus X. And then for I2, 0.15 minus X. Now, the equilibrium constant, which is given as 0.016, does not change. So Lachatier's principle talks about how if you change the volume or if you change the reactants or product concentration, the equilibrium constant does not change. The reaction may shift and the concentrations will be different, but the ratio of those concentrations will stay the same. Furthermore, if you have an endo or exothermic reaction and you change the temperature, then it does change the equilibrium constant, but that's a different story. And we have an example later on. So let's finish this one up. So the equilibrium constant will stay constant. It'll be 0.016. And it's going to equal, it's too thick, we'll do that. It'll equal the concentration of I2 at equilibrium or at the new equilibrium, which will be 0.15 minus X. Minus X times H2, which is what we're looking for. So 0.202 minus X divided by 0.6 plus 2X, and that will be squared because the coefficient for HI is 2. So again, I'm not going to do this one on screen, but you can solve for X using the quadratic formula, and then you can solve for the H2 concentration at equilibrium, which would be 0.202 minus whatever you get for that X value. So I strongly encourage you, try this one on your own. This is a relatively difficult one, but it's not something that is beyond your level. So you should understand how to do this one. Okay, moving on. Now we're talking about Lachatier's principle conceptually. Now you have this reaction, and oh, look at what I see. I see a solid and a solid. So keep that in mind. And our Kp is 0.1 or 1.16 at 800 Celsius. The system is set at equilibrium. There are 2 moles of CaCO3, 6 moles of CaO, and the CO2 pressure is 1.16 at 800. Which of the following produces more CO2 at the new equilibrium? All right, so let's look at it. Which one produces more CO2? So in which case does the reaction go to the right? Let's look at this one. Moles of CaCO3 decreases. All right, this is a solid. So is CaO. Any increase or decrease in concentration of the CaCO3 or the CaO does nothing to the direction of the reaction because they are not in solutions. So we can automatically get rid of all of these because they talk about the amount of CaCO3 and CaO. Anytime you see a solid or a pure liquid, they do not count at all in the equilibrium expression. That is why if you look at Kp is 1.16. Look at the pressure of CO2. It's also 1.16. What that means is Kp is just equal to the pressure. I put concentration brackets, but I mean pressure. The pressure of CO2 over 1 because there's no reactants that count and there's no other products that count. And that makes sense. The partial pressure has to be the same as Kp for this to work. So let's look at the other options. And if you didn't understand what I just said, you can rewind it and slow it down if you'd like. Next, the volume of the container increases. And they even give you a little hint, the pressure drops. All right. So if the volume increases, think about that. Then the gases have more room to move. And that means their pressure decreases. Once their pressure decreases, they want to react in such a way that allows the pressure to increase to its equilibrium ratios. It doesn't like to be too high pressure, too low pressure for the mixture. So for our pressure to decrease, we usually want to go in the direction of the most gas moles. So I'll write here most gas moles because we want to restore that pressure that we just lost. And the most gas moles happen to be in the products because there is only one gas, making E the answer. And then F is not the answer because the volume decreases, which means the pressure increases, which means it'll go towards the left where there is the least amount of gas moles. So That's a more tricky example, but keep that in mind. All right, next one. We have this reaction, and it is exothermic, right? Because the delta H is negative. So keep that in mind. Select one or more. The reaction is endothermic. That's not true. The reaction is exothermic. That is true. Increasing the temperature increases the equilibrium amount of ammonia. All right, let's see that. So if you increase the temperature, now let's rewrite this equation. If it's exothermic, that means heat is released. So we can write in our products plus 92 kilojoules. If we increase the temperature, that means we're increasing this, then the reaction is going to the left. So that means will it increase ammonia? No, it won't. It will decrease ammonia. So that's not the answer. Decreasing the temperature will increase the equilibrium amount of ammonia. That's true, because if we decrease heat, we can consider it as a product in this case, in an exothermic reaction. If you decrease heat, in order to regain that equilibrium of heat, the reaction will go to the right, and the equilibrium amount of ammonia will increase. So that's good. Changing the temperature has no effect on the equilibrium amount. That's not true. Okay. Moving on. Last one. So we have this reaction. Pick the correct statements for the reaction. All right. So more Lacombes principle. And keep in mind, look, you have silicon dioxide as a solid. This means it's not going to count. And we have pure liquid water. Not going to count. So removing CO2, the equilibrium shifts to the left. So where's CO2? Right here. If you remove it, shifts to the left. That's true. Once you remove it, the reaction wants to recover the amount of CO2 that's lost, and it'll shift to the left. So that's true. Removing CO2, no change. That's not true. Removing CO2 to the right, not true. Adding CO. So if we add CO, that means it also go to the left in order to restore that balance. So that's true. Go to the left. And no change is not true, and to the right is not true. Adding silicon. Now, in this case, silicon dioxide is a solid. So it won't go to the left. It won't go to the right. It'll be no change. So that is your answer. That's the last one I have here. If you have any questions, feel free to comment below, and like and subscribe as always. Thank you for listening, and I hope you learned something.